Good afternoon. I'm Professor Sever, and welcome to my video notebook series on linear algebra. This is part 2 of 3 in this notebook series. Today we are reviewing notebook number 1 on linear equations and linear systems. Let's begin. Okay, continuing. So in this course, we're going to use matrices a lot. So what we're doing is we're introducing this notion of a matrix, but in the context of a linear system. So first, kind of doing it out of order, a matrix is a rectangular array of numbers. So this matrix has 3 rows and it has 3 columns. The rows are horizontal, the columns are like the columns on a house, they are vertical. So let's just look at this system, and again, this notion is kind of predicated on the fact that you would already know what a matrix is. I just briefly went through that, but the essential information, which are really the coefficients and the constants, of a linear system can be recorded compactly in a matrix. Okay, so if we look at this linear system in x1, x2, and x3, then the coefficients, and that's the coefficients of the variables, which are here all on the left-hand sides of the equal signs, can be represented in this matrix. And notice how we do them in order. If we lined them up, now here in the second equation, there's a 0x1 term. So reading downward, what are the coefficients of the variable x1? There would be 1, 0, and minus 4. You can see I have those coefficients here. What are the coefficients of all the x2 variables? Negative 2, 2, and 5. And again, you see I'm placing these in the same order that the equations were in. First equation, second equation, third equation. These are the coefficients, first row of x2 now. First row, second row, third row. And again, doing x3, the coefficients would be 1, negative 8, and 9 respectively. And you see I have those as the entries in my third column. Such a matrix, which is derived from the coefficients of the linear system, is said to be the coefficient matrix of that system. Okay. Now you'll note I did not bring into play the constants, and that's done over here. So now an augmented matrix consists of the coefficient matrix that we just discussed, but we also include in the same respective order the constants which occupy the right-hand side of the equals, 0, 8, and minus 9 respectively. Now sometimes we draw, to emphasize that it's an augmented matrix, we draw a vertical line here indicating that the matrix is augmented. However, the absence of the line would not be enough to state unequivocally that the matrix would not be augmented. So if we have the line there, it's certainly an indication that you're dealing with an augmented matrix, but the line doesn't have to be there in general for an augmented matrix. So be cautious. All right, the size of a matrix tells us how many rows and columns it is. It's referred as M by N, but the thing to note is it's the row by column. Okay, so this has 1, 2, 3 rows, 1, 2, 3, 4 columns. This would be a 3 by 4 matrix. Okay? And each entry in the matrix can be named by its position. So if I were to look at the number 1 in the upper left corner, it's in the first row, first column, so it's in the 1, 1 entry. And we say it in the same order. When I say 1, 1, then the first one I said was indicating the row number. The second one I said was indicating the column number. So let's look at the number 5. There's only one number 5 in this matrix. Where does it live? It lives in the third row, second column. So it's in the 3, 2 entry. 3, 2, third row, second column. And in this course, we're going to develop a strategy for solving linear systems. And you recall what solving is. Solving is the process that you undertake to find the solution set, to find the solutions of the system. We're not there yet. That's actually going to be in the next section of this course. So as a problem, you can write out all these 12 entries by their respective positions. For example, negative 9 is in the 3, 4 position. And if you want, you can go through and write that out for your own edification. It will be an interesting exercise. All right, let's look at this next example. Let's consider this augmented matrix, and immediately I'm telling you it's augmented here in the language, and of course I'm showing that as well with the vertical line. Again, if this vertical line wasn't here, we would still understand it was augmented by this description. What are the variables of the system? Well, first, how many variables do we have? Well, there would be 4. There are 4 columns on the coefficient side. So we would either say they are x, y, z, and w, or it might be better to say x1, x2, x3, and x4. Those are our variables. Write the associated linear system. We will do that here, and I've presented it thusly. And I would write it as rows. Each row of the augmented matrix corresponds to an equation. So I would write the equation corresponding with the first row, and you can see it's here. I would write the equation corresponding to the second row. You can see it's here. And I would write the equation corresponding to the third row. You can see it's here. And when you consider these equations together, then we have a linear system. Show that the ordered quadruple, -2, 4, 2, 1, is a solution to a system. To do this, we have to plug it in to each of the 3 equations in turn to show that it is a solution. If it's not a solution, if we plugged it into the first equation and we did not get a true statement, it would not be a solution to that equation, and then consequently it would not be a solution to the system. In this case, we would not need to plug it into the remaining equations. We would have our answer already. But ostensibly, we need to, if this is in fact true, we would have to show it on all 3. You can't just plug it into one, get a true answer, then presume, or assume rather, that it would be a solution to the remaining equations in a system. Okay, so let's do these. We do the work below, and we'll see that -2, 4, 2, 1 is a solution. We have a similar question about the ordered tuple or quadruple 1, 3, -1, 0. It is also, as you can see, a solution to the system. So is the system consistent? Well, the answer is yes. The answer to C alone would have told us the answer is yes. If you have a solution to the linear system, it's consistent. That's what it means. So now, what about the part F? Discuss the nature of the solutions. Well, I have 2 solutions to the system. Can I have only 2 solutions? Or can these be the only 2? The answer is no. Our first theorem tells us that it's no. You can have none. We know it's not the case that you have none because I have 2. You can have exactly 1. We know that can't be the case because I have 2. So what is it? What's left? We must have infinitely many. So therefore, there must be infinitely many solutions to this system. Again, we will find and describe those solutions in a subsequent lecture. Okay, introduction to row operations. There are 3 types of elementary row operations, and remember, a row in an augmented matrix corresponds to an equation, and when you look at these or consider these operations, these will be familiar to you in terms of manipulations that you would make when dealing with equations. So type 1, scaling. You can multiply a row by a number. Okay, so you can say, I'm going to take row 1 and multiply it by 2, okay, or by a half. And we see that here. So we multiply row 2 by a half, and then we'll see that the first and third rows you're not changing, because if I say multiply row 2 by a half, that means you're leaving the first and third rows unchanged. And then you change the second row and you multiply each of the entries in the second row by a half. That's scaling. You scale each of the entries in the second row. And you see the result here. Type 1, so notice here's the operation. K is the number that you're multiplying by, and in that example it was a half. So we're saying 1/2 times row 2, and the arrow says to yourself, put the result of this operation into row 2. So you're going to replace the original row 2 by the scaled version of row 2. Row interchange. So type 2, and we do interchange. We can just interchange swap row J and row I. So in this example, we're going to swap row 1 and row 2. So in this example, we're going to swap row 1 and row 2. Row 3 stays the same. So what would the new row 1 be? Well, it would be the old row 2, and the new row 2 would be the original or old row 1. This is just a row interchange. Type 3, we call this a linear combination. Now this is very important to get the kind of the order right. If you did it wrong, you would still get an equivalent row equivalent matrix, but it may not be row equivalent by one step. And this will be important when we deal with elementary matrices in the subsequent section. So in this example, take a number like 4. We're going to we'll multiply 4 times row 1. We're going to add that to row 3, for example, and then the row, now notice row 3 or row J here is the row that we're not scaling, and you add that to row J. So here in the example, it'll be 4 times row 1 plus row 3. Put that result back into the row 3. Okay, and we see that here. So we have 4 row 1 plus row 3, put the result into row 3. Well, immediately we can see we're not changing rows 1 and 2. Now be careful, this is a temporary scaling. You're not actually scaling you're not scaling row 1 by 4. You're doing that kind of mentally, so to speak, and I'll show you how to write this. So you do 4 times row 1 plus row 3. Think of this as being a side computation. You do all this on the side. Then the only row that you're changing is row 3, and you replace row 3 with that product. And it should be easy to see. We can do it mentally. Notice we can do them one column at a time. So 4 times 1 plus negative 4. I'm going to multiply row 1 by 4, and I'm going to add that to row 3, but I'll do it one column at a time. So I only have to think of one operation at a time. 4 times 1 is 4. 4 plus negative 4 is 0. See? 4 times negative 2 is negative 8. Negative 8 plus 5 is negative 3. 4 times 1 is 4. 4 plus 9 is 13. I have that here. So you can see how you can do this mentally. Now if there were fractions involved, then yes, you might have to write it down, but in this simple example we can just do it mentally. 4 times 0 is 0. 0 plus negative 9 is negative 9. And that's how we get the new third row. And these are the only 3 types of things we will do with linear systems, and they're the only types of operations that we will do with matrices. These will be our 3 primary operations for solving linear systems. Thank you for watching part 2 of Notebook 1 in this notebook series. This video notebook lecture will continue in part 3. So we look forward to seeing you there. I hope you enjoyed part 2 of this notebook series. I'm Professor Sever. Thank you.